Cool. So solution chemistry. We're going to be learning about different types of solutions. So a solution is basically a solute and a solvent get mixed together, meaning a solute is a particle or particles, and then the solvent is the media that the particles are put into. So in general chemistry, we always like to use water as the universal solvent, but there are many other solvents. So solvents could be oil, could be vinegar, it could be different types of organic solvents, benzene, hexane, dichloromethane are some very common ones in organic chemistry. But for general chemistry, we just talk about water for the simplicity of it, and it's the universal solvent is what they call it. So when you have a solute go into the solvent to make a solution, what happens is it dissolves, right? And it could dissolve or it could not dissolve, but something dissolves. It could be ions, it could be different entire molecules like sugar. And we'll talk about the difference of those types of solutions. And they're all homogeneous mixtures. So that's what a solution is, a homogeneous mixture. Because if you dissolve sugar or salt in water, you don't see it anymore, and it's evenly dispersed throughout the entire solution. Meaning, if you took a sample of it from different places in the solution, you would end up with the same chemical makeup, the same density of particles in each sample. So there's a different way, well, there's a reason why these things happen, these things. By things, I mean, there's a reason why that sugar and salt dissolve into water and other molecules don't, and sugar or salt do not dissolve into oil. There's a reason why this is. And that reason is because water is polar. So polar is a key word, which once we learn about the Lewis structure, electronegativity, we'll learn more about polar. But basically polar means like polar bear, right? And water has to do with water, is that normally when we talk about covalent bonds, right, we don't really consider charge. There's no ions, there's no oxygens -2, hydrogens +1. We don't think about that when we think about ionic or covalent bonds. We just think, oh, the two nonmetals bond together. But for polar molecules, what happens is they bond together, and for covalent, we know it's a sharing of electrons. That sharing of electrons is uneven. So if you have, so I'm gonna move this thing right there, pen. So in this covalent bond right here, between the oxygen and the hydrogen right here, there's 2 electrons. Someone's joining. There's 2 electrons. And those electrons in normal covalent bonds that are non-polar, they're equally distributed. There's one here and one here. They're equally shared between each of the atoms partaking in that bond. But for polar molecules, there's an uneven sharing, meaning towards the molecule that's more electronegative, which we'll learn about that in later chapters, but towards the molecule that basically wants the electrons more, the electrons will actually go towards that molecule. So the electrons in a hydrogen-oxygen covalent bond are actually very close to the oxygen. So hopefully that makes sense. Always ask questions in case it doesn't make sense. So basically a polar molecule is where it's a covalent bond that the electrons are unevenly distributed between the 2 elements. And this happens a lot of the time. Most covalent bonds are either polar or slightly polar, where there's an unequal distribution. So what happens due to this unequal distribution is you have more electrons located towards one of the elements. If that's the case, and you want to compare both of their charges, even though for covalent bonds, we don't really talk about charges, in this case you can. You could say that if you want to talk about charges, I would give the oxygen, hold on, where's my pointer? There it is, okay. So you can give the oxygen a negative charge, and you can give the hydrogen a positive charge, because all the electrons are located towards the oxygen in the covalent bond. And then there's a lack of electrons towards hydrogen. That lack of electrons makes it positively charged. because the other one is negatively charged. So comparing the two, the positive would be on the hydrogen. So this, in an entire molecule, this phenomenon is what makes the molecule polar. Now, also in water, they create hydrogen bonds, but hydrogen bonds aren't the reason why things dissolve, really. It's really because of polarity. Hydrogen bonds, we will talk about more in detail when we get to intermolecular forces. So those molecules being polar, we know now that we know that the solvent is polar, meaning water is polar. Why exactly do salt and sugar dissolve in those polar solutions, in those polar solvents? And here is why. There are two reasons. One is when we're talking about ionic solutions, ionic compounds, such as salt, NaCl, MgSO4, right? Any ionic solution, any ionic compound that we talked about so far, this is the reason why it dissolves. It dissolves. And it's different from things like sugar, things that are not ionic. And I'll explain what's going on here. So it's important for you to understand molecularly what happens when things dissolve in the molecules itself, the molecular behavior. So you drop a piece of salt in water. And if you drop the piece of salt, it's not just one Na and one Cl, it is a bundle. This is a under-exaggeration and under-appreciation. There's actually billions of them, of ions, of plus and minus ions. So you have the positive charged sodiums right here and the negatively charged chlorines as the bigger ones. And what happens is, it's actually the opposite. Sodium's bigger, chlorine's small. What happens is the water molecules with their partial positive and partial negative charges, let's say partial positive here, partial negative over there, they attack the salt molecule. And the way they attack is, you can see that the chlorine, or we'll look at the sodium first. This sodium that I just circled, that is been attacked already and taken away from the rest of the molecule, all of the oxygens from water are facing it. Meaning the negatively charges of the oxygens are getting close to the positive charge of the sodium. And that's exactly what happens. So it is a charged induced attack of the salt molecule. So the negative charges from the oxygen attack the positive charge from the sodium, thus ripping it away. It actually gets ripped away. So you imagine all these water molecules there's billions of them, they kind of dig into the structure of the sodium chloride molecule, and they rip apart the sodium and they drag it away, and they engulf it and drag it away. And the same thing happens with the chlorine. But since water is polar, it has the ability to do this. If you had a non-polar solvent with no poles, meaning positive or negative ends, to bind to the sodium and the chlorine respectively, this would not occur. The fact that water is polar, and you have other polar solvents too, makes this possible. And you can see how the chlorine over here, the chlorine over there, same thing happens, but the positive charge ends of the water, meaning the hydrogens, are the ones that attack the chlorine anion. So you have this dual mechanism going on, either the positives from the hydrogens attacking the chlorine, or the negatives from the oxygen attacking the sodium. Both of them are happening at the same time in a polar solvent attacking a ionic compound. So that's molecularly what happens. Any questions on that? And this is called an electrolyte once this happens. And we'll learn about the different types of electrolytes in a couple slides, but an electrolyte is basically something that has the ability to conduct electricity because you have these free ions that are in the solution. They have the ability to to move electrons along the charge, or with the charges. So any questions on that? No? Okay. All right. The second case is when you have a non-ionic solution, meanwhile, or otherwise known as a non-electrolyte. Now, sugar is a non-electrolyte, even though it dissolves in water. Now, what this means is you dump sugar into water, like even a crystal of sugar, which has many billions of molecules on it. What you'll see is in molecular, if you look in a microscope, well, you really can't see this in a microscope either, but if you look at the molecular level, what you see is that the water molecules will engulf each individual molecule of sugar. They will not break apart the sugar molecule into ionic components like was done with the salt. And that's important because the sugar molecule, sucrose, is a pretty big molecule. There's no really, and it's all covalently bound. So, with sugar, but let's draw sugar. So a sugar, why is my pointer really small? Anyway, a sugar looks like this. You have OH, H, C2OH, OH, H, OH, H. There you go, that's a little bit better. All right, so basically with the sugar, you have, it's a big structure and you have more OHs in other places too, but it's a big structure, it's a ring, and it has a bunch of OHs on it, hydroxides. And these hydroxides make it make it polar. The more hydroxides you have, the more polar you have, because you have that same oxygen-hydrogen covalent bond like you see in water. So basically you have a big structure, that's a sugar, that is covalently bound, and it's polar. So you can't break it apart by ions, because there are no ions, because it's covalent. And it's polar, meaning it can stick to, or it can be miscible. Miscible means it dissolves into. It can be miscible into water, or any other polar solvent to some extent, because of these partial charges. So all these oxygens will have a partial negative, all the hydrogens will have a partial positive, and then the water molecules will attack. So this water molecule will go here, the oxygen will attack the hydrogens will attack the oxygen. So it's the same concept as ionic, but the molecule isn't splitting apart, and there's no charged ions being created. So that's why we call it a non-electrolyte, because there's no charges involved. Even when it's dissolved, there's no real ionic charges. Any questions on that or both of those, the comparison between those? No? My internet's still good? Good. All right. We're rolling. So we're going to learn about molarity towards the end of the slideshow, but basically you can determine, or basically molarity is a determination of concentration. So we'll learn about how to calculate it later. It's basically moles over liters, right? The moles of your solute divided by the liters of your solution. And you can have different solution concentrations of different solutes. So you could have for example, like this example, a 0.5 molar solution of cobalt-2 nitrate. Where's the thing? There it is. Wow, it's so tiny. There you go. So you can have this, which is a 0.5 molar solution of cobalt-2 nitrate, and it's cobalt-2, remember, because nitrate is -1, there's 2 of them, so then cobalt has to be +2. But anyway, that's a solution, right? That means there's 0.5 moles of it per liter of the entire solution, and also it's in water. But basically, what we're trying to talk about here is that when the ionic compound dissociates, or when it dissolves and becomes its ionic components, it's not always a 1-to-1 ratio, like NaCl. So NaCl breaks up into, we know, Na plus and Cl minus. But for cobalt-2 nitrate, it breaks up into 1 cobalt-2 plus and 2 NO3 minus. And it's important that when we write these dissociation equations of electrolytes, that we put the 2 in the front. You notice how it's NO3 2? Here we have 2 NO3. The reason why is because molecularly it makes sense. If you wrote NO3 2 as its own thing, that's saying you have 2 NO3 molecules bound together. That's not true. That's not how that happens. You could have 2 free-floating NO3 minus ions, one of them over here, one of them over here. So that's totally possible, but they're not bound together. That's why you don't write NO3 2 like it's written here. In this case, with the cobalt-2 nitrate, they're actually bound together. both of them are bound to the cobalt. So what we're trying to say is in a 0.5 molar solution of cobalt 2 nitrate, you actually have 0.5 molar of cobalt and 1 molar of nitrate, because there are 2 nitrate molecules per 1 molecule of cobalt 2 nitrate. So basically inside each molecule there are ratios, just like we have that. If you try to figure out the mass percent of iron in Fe2SO4 or Fe3SO4 you would get the molar mass. Then you'd multiply iron by 3, because you know there are 3 irons per 1 molecule. This is the same concept. You have 2 nitrates per 1 molecule. Therefore, you multiply the entire molecule's concentration or amount by 2. And then you get that answer. So hopefully that makes sense. Ask questions if you want. Okay. Next, so you have electrolytes. Now, electrolytes, there's 3 types of electrolytes. There are strong electrolytes, there are weak electrolytes, and then there are non-electrolytes. So all 3 of them dissolve in water, but they have different behavior. So you can see that in this example here, you put in salt into a water solution, and you will have an electrolyte. Just like we talked about before, when the sodium and the chlorine ions are getting attacked by the water, you're getting an electrical charge being conducted, or being able to conduct. And and what that happens is if you hook up an anode and a cathode, you can actually get a light to turn on, and you put it up to a battery. The transfer of electrons from the cathode, or from the anode to the cathode, what happens with that is you get an electrical gradient. The electrical gradient creates a current. The current runs the battery, which runs the flashlight, so that's, or the light bulb, and that's basically what happens. But in a sugar solution, meaning something that is a non-electrolyte, you're not going to have any part of the sugar dissociating, just like we saw here. None of the sugar is dissociating from itself, and you end up with just the sugar molecules by themselves with no charge, and they do not conduct electricity. And you will have, if you put an anode and a cathode in there, no electrons will be transferred and nothing will happen. So you end up with a non-electrolyte solution. Then there are things called weak electrolytes, where basically the electrolyte phenomenon happens, but it's very weak, and it's only a very small percentage of the molecules dissociate, which we'll get into that now. So, like I said, a strong electrolyte, you can imagine it's where all of the molecules dissociate into their ionic components. And really it's most ionic compounds and strong acids. That's the key. It's most ionic compounds and strong acids. By most, I mean some ionic compounds aren't soluble in water. Well, I thought they all were, but not all of them are. And we'll talk about that once we talk about the solubility rules and solubility in general. But some of them aren't. So strong acids, we'll learn about those too, but they're there, and they completely dissociate. They have, remember, acids have hydrogen, right? They have hydrogen, and for like HCl, CO3, or H2CO3, they have hydrogen in front. So what happens with these strong acids, well, this is not a strong acid, just HCl is, you have the hydrogen breaks off and it creates H+, the Cl breaks off and you create Cl-. So that is what, and that will happen to 100% of the molecules. Every single molecule of HCl that will happen to. But for H2CO3, which is a weak acid, you'll have maybe 1% will be H+, 1% will be CO3 2-. The rest of it, 99%, is going to be H2CO3 undissociated. So most of it does not dissociate. And that's where we have a weak electrolyte, which substances that dissolve mostly as molecules, but partially dissociate into ions. You have weak acids, and also there are some solutions that just conduct electricity poorly. There are some ionic compounds that what we call sparingly soluble, meaning they don't dissolve that much. So that's that. Okay, so water, not water, well, this involves water, but acid bases. So acid bases, we have, in essence, we have acids which have a hydrogen in the front. The bases usually have an OH, a hydroxide, and they mix together and they create some kind of salt and water. So that is a definition of acid-base neutralization, which we've talked about when we talked about balancing them, but now understanding what they actually are. So in the reaction of an acid with a base, H plus from the acid combines with the OH minus from the base to make water. That happens all the time. So you can kind of think about it as the cation, even though it's not really a cation because it's hydrogen, the plus from the acid, the hydrogen, and the anion, which is the hydroxide, from the base, react together to make water. And then the remaining cations and anions, in this case, sodium and chlorine, go together to make a salt. So that is what happens. And you have, and you can have many different types of salts. So salts denote any ionic compound. You can have, let's do another reaction. So you have H2SO4 plus MgOH2. And if this acid-base reaction goes through, you have HOH, which is water, plus MgSO4. MgSO4. And this is not balanced. We can balance it. H2, there's only one H here. OH2, there's two, so you basically just put two there. That's a quick one, but the two there makes everything work. There's one magnesium, one sulfate, good. So you can see how in every acid-base reaction, it will happen the same way. You'll have a positive, or sorry, you'll have a hydrogen meet up with an OH to make water, and then the remaining stuff, the remaining ions, will go together to make a salt, which is sodium chloride in this example. Okay, so strong acids and strong bases. Now, what makes an acid strong? What makes it weak? And this actually, the answer for this is the same thing that makes electrolytes strong and weak. So for strong electrolytes, which are strong acids are incorporated into strong electrolytes, 100% of the molecules ionize. Ionize basically means split apart. So strong acids, strong bases, most ionic compounds are strong electrolytes. That's something you should write down. So I'll write that down. So strong acids, I can't write, strong acids, strong bases, and most ionic compounds are strong electrolytes. Okay, that's a good thing to know. Now, basically, if you have, or I said this already, but if you have 100 molecules of HCl, every single molecule will dissolve. You have 100 H plus ions, 100 Cl ions, and it will be very electrically conductive, and it will dissociate completely. It will be a strong acid. Now, a good question some of you might have is, oh, how do you know if it's a strong acid or not? I have a really good mnemonic for that I invented, actually. And this will be on my, once I make that crashchem.com thing, this is going to be one of the key things, because no one knows what I'm about to tell you. It's not in any textbook, so it's unique. So that's what I have. That's the edge over Khan Academy. I have a lot of these little things that either I invented or somebody I know invented that that are unique. Anyway, so we know that they're strong electrolytes. Now there are acids that ionize partially. Acids that ionize partially, which are called weak acids. One of those weak acids is HF. So HF dissociates into H plus and F minus, but very, very small percentage of the time. And you see how small of a percentage that is. And look at this, if you have 100,000 molecules of HF, you can expect only one H plus ion, only one. So that's 1 out of 10,000 or 100,000. 1 out of 100,000. That's not even, I said 1% before. It's not even 1%. It's 0.01 for 0.001% or whatever that is. So that's crazy. So something else you might notice is that you have a double arrow here. So this double arrow represents equilibrium. So because the reaction does not, for the reaction for weak acids, weak bases, so I'll write this down also, that for weak electrolytes, it's easy because only weak acids and weak bases are weak electrolytes. There aren't really many other substances that have this phenomenon of only partially dissociating at a very small amount, other than weak acids and weak bases. But this double arrow, move it over here. So this double arrow represents equilibrium. In the first example, when we're talking about strong electrolytes, there is no need for equilibrium because you have all these reactants, 100% of the reactants become all products, and there's no going back. Here, for weak acids and weak bases and weak electrolytes in general, once the reaction is said and done, once it reaches equilibrium, there is a concentration of the reactant still, because not all of the reactant reacted, only a very small percentage of it did. That means most of it is still in the reactant side, most of the material. You have a small amount in the products. So you're going to have every single molecule in the reaction is going to be present at equilibrium when the reaction is done. This means there is potential for H plus and F minus to rejoin from random motion in the cells, or not in cells. I'm talking about biology. I'm thinking biology. I'm talking about cells all week, and I say cells. I meant in the solution. So H plus and F minus have a chance to rejoin in the solution, which is possible. They might, and they will. That's why we have backwards arrows. They will rejoin, and they'll go from what we call the reverse reaction. They'll go from products to reactants. And then the vice versa will also happen. Once that happens a couple times, maybe some of these HF molecules will slowly become H plus and F minus. So you have this equilibrium that it goes either way, but you know that most of the molecules are in the reactant phase. They're still HF because only a very small percentage of them dissolve into H plus F minus. Okay, good. Any questions on that? My internet's still good, knock on wood. All right, where'd my cat go? She's gone. Okay, so here you can see different electrolyte solutions. You have a sugar, and this is what sugar formulas look like. You notice they're large, C12, H22, O11, where there's not really a place for ionization. You can't look at this as the basic chemist can't look at this and be like, oh, it ionizes and you take an OH out and it becomes a charge. No, it's just a heavy molecule. So chances are it's gonna be a non-electrolyte. That's the Chem-1 rule of thumb is if you see a heavy molecule like that, like a long chain or something, chances are it's a non-electrolyte. Then you have these ones, which aren't necessarily that long, but you have, this is acetate, the acetate ion, C2H3O2. You put an H in front of it, H acetate becomes acetic acid. So acetic acid is a weak acid. And what happens is you have a weak electrolyte that is resulting from it, and you have a very small electrical current. And then you have strong electrolytes such as our good old NaCl, which will create a large current and it will power the light bulb. Okay. Yeah, any questions up until that point? Because now we're going to talk about solubility rules and solubility of different ions. No, so you have your strong, your weak, and your non-electrolyte. And we'll talk about, actually, I guess now's a good time to talk about acids and bases. Yeah, so, all right. So in terms of characterization, like your job and on exams would be to, I give you different molecules and be able to just tell me which one's a strong electrolyte, a weak electrolyte, or a non-electrolyte. If you see a sugar, or I could repeat myself, but you should have a good idea of how to do that with, if you see a longer molecule, all right, it's probably a non-electrolyte. If you see something with an H in front of it, you're like, it's either a strong acid or a weak acid, I don't know, but you're about to know. Something ionic, you're like, all right, it's probably a strong electrolyte. So if you're there right now, that's good. Now let's get into strong acids and weak acids, just so we understand, and bases too. But just so we understand and we have a full picture of how to characterize electrolytes into strong, weak, and non. So for strong acids, here is the thing that I invented. So it's copyrighted. It's not really copyrighted, but it will be once it's on crashchem.com and I'm making millions. But here is how it goes. I'm going to write them down and I'm going to say them. And if you've ever heard of this before, please let me know after I say it, because that makes the most sense for me. No. I know that all the numbers are supposed to be subscripted. And then weak acids, everything else. Strong bases, group 1A, 2A, hydroxides, weak bases, everything else. All right, so here is all you need to know. Here's all acids and bases summarized into one slide, very easy to remember. The strong acids, here's how you memorize it. Hickel, Hibber, High, Hino, Hiklo, Hiso. What? That's crazy, right? But I'll say it again. Hickel, HCl, Hibber, HBr, High, HI, Hino, HNO3, nitric acid. Hiklo, there's actually two Hiklos. See HClO3, HClO4. Hiso, Hickel, Hibber, High, Hino, Hiklo, Hiso, H2SO4. They're not in any order, but this is just a cool mnemonic that I invented, me and another friend in college invented, that nobody knows about. And you memorize that, you not only memorize the strong acids, but everything that is not on that list is a weak acid. In terms of basic acids, not organic acids, there are some that are strong, some that are weak, but mostly everything else is weak. These are the most common strong acids. And there aren't, I tell you this, in Chem 1 and 2, there aren't any strong acids that you'll get that are not on this list. Because there are crazy ones, sulfonic acid, other things like that are insane. But that's like research level stuff. You don't do that in Chem 1 and 2. So any questions on that, on strong acids and strong base, and strong acids and weak acids? Hickel, Hibber, High, Hino, Hiklo, Hiso. And if you memorize that, boom, that's it. And you know all the strong and the weak. So that'll be like a 30-second video on crashchem.com. I do have it on the Instagram, so if you want to see that again, it's there. Okay. No questions? All right, we'll keep going. Then for strong bases, it's very simple as well. Group 1A and 2A hydroxides. So that means if you have CaOH2 is not really that soluble, but it's still considered a strong acid. Then you have KOH, KOH, NaOH are the main ones. That's the strongest bases. Did I say acid first? Yeah, I think I said acid, but bases. MgOH2, things like that. So if it has a group 1A or group 2A metal, it is considered, with a hydroxide next to it, it is considered a strong base. Weak bases, everything else, meaning iron hydroxide, cobalt hydroxide, zinc hydroxide. And by also another thing, group 1A, 2A, I don't mean hydrogen. Obviously, if you have a hydrogen with a hydroxide, that's water. So group 1A and 2A, metals. That's important. Metal hydroxides. Also, for weak bases, there's something that we should know. Ammonia is the main weak base. So any exam, if they want to give you an example of a question with a weak base, guarantee you they're going to use ammonium because that is the most common weak base there is. Other ones are, like I said, everything else. So group 3A, aluminum hydroxide, transition metal hydroxides, other things like that. There are other ones, but technically calcium carbonate as a weak base, but not important. We're just talking about the hydroxide ones. Okay, any questions on that? On strong, weak acids or bases? All right, if not, we'll keep going on. So now you should have a really good idea of characterizing electrolytes because you know exactly what to look for, or when you study, you will know exactly what to look for when I give you a molecule. Oh, if it's big, it's this. If it's a non-electrolyte, if it's smaller and has an H in front of it, it could be strong or weak. This is acetic acid. Pickelhibber high acetic acid. No, acetic acid is not on the list. Therefore, it is weak electrolyte. NaCl, ionic, strong. So most of the ionics are going to be strong. Another thing that will determine, or that will help you determine if they're strong or weak, is the solubility rules. So remember I said most ionic compounds are soluble in water. However, not all ionic compounds dissolve in water. For example, silver chloride remains solid and appears white powder at the bottom of the water. In general, a compound is termed soluble if it dissolves in water and insoluble if it doesn't. So basically, 90% of ionic compounds dissolve in water. Not all of them though. And there's actually a little trick for that. There's this, which we're gonna talk about this in a second, but look at that. These are solubility rules. Oh my God, that's so daunting, right? There's an easy way. It's probably not soluble. Probably not soluble if it contains lead, silver, mercury, or I think that's it. Yeah, lead, silver, or mercury. If you see those in one of these equations, make that a red flag in your head that it may not be soluble if it has lead, silver, or mercury. In some cases it might. For example, if you have nitrate, every single nitrate is soluble. Lead nitrate, silver nitrate, mercury nitrate, they are all soluble. But sometimes these are the key ions where you mostly get non-soluble or insolubility. But we'll talk about that more when we get to the rules. So here's, you can just visual representation. You can see silver nitrate. Silver nitrate is definitely soluble, and it's a strong electrolyte, just like every other ionic solution. And you see the NO3 separates from the Ag+, and you get a good solution. Then if you have silver and chlorine, silver chloride, you don't get that. It is insoluble. And the reason why that some are insoluble and some are soluble is because of the strength of the ionic bond sometimes, and also just the energetic stability of it. Sometimes they just don't like to become ions because they're more energetically stable when they're balancing each other out. So silver and chloride, it's very energetically stable molecule, and even in the presence of water, water can't get in there and attack. Just like we saw for the strong electrolytes, or really anything that dissolves, the water molecule attacks the different, it attacks the molecules. And in ionic case, it attacks the ions and breaks them apart. But in insoluble ionic compound, yeah, it's tough to say. Insoluble ionic compounds, you do not see that happening. They stay as one thing. Okay, I feel like there's no questions so far. Is there any questions? No? Maybe, hopefully you didn't fall asleep. Everybody still here? Okay, 27 of us, good. My internet's still on, all right? Am I talking to myself? Okay, good. All right, so next, the solubility rules. Now there is a set of rules that, yes, you need to know. and they will not be given on the exam. Oh no, they'll not be given on the exam. But there is a very easy way to know them. And also, if you're thinking, oh, I could just like have them up in my notebook. You could, but it's not going to help you because you're going to need to know these more for Chem 2. And Chem 2, if you're taking it in the fall, it might be in person. It probably will be in person to some extent, like hybrid or something. No one knows yet what they're doing. Or if they do, I just haven't been reading the emails. But yeah, so you need to know them. And they can be simplified. So here's how I'm going to simplify them. The first two rules, know them. If you have anything in group, let's say this. Most of the 1+ charge cations that are in group 1A are soluble. Lithium, sodium, or you could just make up that's a stupid thing I just said. That's a very convoluted way of saying it. You could just make up a thing. Like, let's make up a thing right now. Make up a thing. So that's too thick. Let's see, make up a thing. I don't know. Nalik, NH4. Nalik NH4 plus. All right, there you go. Nalik. All right, so Nalik NH4 plus. Ta-da. Or Lanak, whatever, Nalik. So there you go. They're always soluble. If you have Na plus in any, you have Na plus and then something hydroxide, we know that is soluble, but Na plus with any anion is soluble. Lithium, same thing. Potassium, same thing. Ammonium, same thing. Then you have, for anions that are always soluble, you have nitrate and acetate. So nitrates, every nitrate is soluble, every acetate is soluble. So these are two really important, these are keys. Because knowing these two can get you the answer of, is this ionic compound soluble for most of them? Then these get a little bit complicated, but let's just break it down. Chlorides, bromines, and iodides are soluble, but they're insoluble with, oh look, the three I mentioned. And then let's just look at the next ones. Oh look, soluble with all ions except, yeah, strontium and barium, but look, the three I mentioned. And then look at this one. Oh, okay, whatever. Let's look at those. So just knowing that if you see a silver, a mercury, or a lead, to raise a red flag, that's a good thing because those are the ions that usually are not soluble when they're in a lot of compounds. When they're in chlorines, bromines, iodides, sulfates, phosphates, carbonates, hydroxides, and sulfides, they are not soluble. So if you see these three with any of these anions, they're not soluble. Very key thing to know. Everything else kind of as a reiterative. So let's look at this, carbonates and phosphates. They're soluble with, yeah, all these four. Nalik, they're soluble with Nalik and NH4, insoluble with everything else. Okay, so basically if they don't conflict with the first rule that all these are soluble, then everything else is insoluble. So, all right, that's not too bad. Then hydroxides and sulfides, soluble with basically everything in 1A, Nalik, NH4, and also calcium and strontium, insoluble with everything else. So if you just remember group 1A, Nalik, NH4, those are the things that are going to be soluble. Everything else, at least for these anions, are going to be insoluble. So there's different ways to get to know these rules, but it shouldn't be you memorizing word for word the rules. You should develop patterns. So like I was just talking about, easy ways to memorize them. Okay, any questions? And I'll be helping you along today, obviously, because you're just learning it for the first time, but you'll need to know it for the exam. All right, so can somebody answer in the chat or with voice? Number 1, this is from the homework, by the way. HCl gas, strong, weak, or non-electrolyte? And we have an answer from Sarah, strong, awesome, good job. Acetic acid, strong, weak, or non-electrolyte? And Marlon, good job for the first one as well. What about acetic acid? Weak, good job, Leslie. Sarah, it's not non. All right, you're 1 for 2, Sarah. But it's not non-electrolyte because, so this is acetic acid. It's written here, but it's also in a different, it's different than the way you saw it before, which is understandably confusing. So where's my pen? There it is. So normally it's written C2H3O2, or with an H in front. That's normally acetic acid. They just wrote it differently. But this, the way they wrote it, is actually more structurally relevant. And what I mean by that is how the structure is written. This is a structural formula. So if you were to write it out, it would be CH3, C, a double bond to the O, single bond to the OH. So that would be acetic acid if you wrote out the structure. And you see how structurally this formula makes more sense. CH3, got it. C, got it. O, got it. OH, got it. Here, you don't really see that. It's hard to go from this, the condensed structure, or the condensed formula, to this. That's why they write it sometimes like this. And then if you want to have acetate, which we know as a polyatomic ion is -1 charge, all it is this. Get rid of the hydrogen, make a -1. So that's the difference between acetate and acetic acid. It's just that hydrogen. Oh, I can move it places. All right, whatever. So good. Here's a good one. So what conducts electricity in metals? 1-word answer. Good, electrons. Awesome. Marie Madeline and Brandon, good job. What conducts electricity in solutions? 1 word. Good job, Brandon. Ions. Good. Good, ions. All right. Yeah, so you guys should be getting the hang of it. Good. Quick answers. All right. Let's move on. So strong acids, we did this already, but just to reiterate that the strong acids are Hickel, Hibber, High, Hino, Hiclo. These 2 Hiclos. It's not perfect, but there's 2 Hiclos. And Hiso, H2SO4. They are the strong acids. The weak acids are everything else not on the list. Strong bases, group 1A, 2A hydroxides. Weak bases, everything else. So, and I'll put for the important one, NH3. That's important. Okay, moving forward. So types of reactions. So now a lot of this is going to be, not a lot of it, towards the end will be kind of a review, because we're going to be talking about redox again. Oh, Marie Madeline has a question. Is O2 a non-electrolyte or a weak acid? O2 is a non-electrolyte. Okay, so we'll be talking about some more reactions. The first one that we didn't really talk about, but we've seen. So all of these we've seen. We've seen precipitation, acid-base, and redox. We've balanced all of them. But for precipitation, we really didn't have time to talk about what it is. We just, oh, here's an equation, balance it. So here's what precipitation is. When you have 2 solutions that are mixed, right? Sometimes you could have an insoluble substance mixed with a soluble solution, or you could have 2 soluble solutions mixed together, 2 ionic solutions mixed together. Sometimes a precipitate forms. Now, precipitate is not like precipitation, like rain. It's actually the exact opposite. Precipitation or precipitate refers to a solid that appears in the solution after a reaction has occurred. So you can, oh, I observe a precipitate in the solution, meaning here you see this yellow cloudy stuff. This isn't liquid. This isn't part of the solution. This is not part of the aqueous solution. It's actually coming out, there is a precipitate coming out of the solution. So you see this sometimes in precipitation reactions. Now, so here's basically what's happening in these types of solutions, in these types of reactions. All right, so you have, let's say you're gonna add this barium nitrate. Let's add barium nitrate, where's my thing? There we go, okay. So let's add barium nitrate, which is right here, to, this is potassium chromate, or is it dichromate? Yeah, I'm right, chromate. So even I need a refresher on the polyatomic ions sometimes. So potassium chromate. If you mix them together, out of all the ions there are 4 ions in those solutions. So you have potassium, barium, nitrate, and chromate. There are 4 combinations of possible outcomes. Potassium nitrate, potassium chromate, barium nitrate, and barium chromate. These are all the possible solutions, or all the possible combinations of cation anion. And yeah, we start out with, that's why these are highlighted, we start out with barium nitrate and we start out with potassium chromate. The idea is that in an ionic solution, and I don't think I said it explicitly, but in an ionic solution, soluble ions will just float around as ions in the solution, like this. That's how they dissolve, they float around. If they're insoluble, if one of the combinations creates an insoluble compound based on our solubility rules, it will form the precipitate, and everything else will be by itself as ions. So here's what we're talking about. Here we go. The thickness of the marker is annoying me. All right, there we go. Okay, so here we're doing that reaction. And in the reaction, let's see, beforehand, you dump in all the ions. These ions are moving very fast. They're making collisions with each other. Eventually, they will come in contact with, maybe they'll come in contact with one, with a positive will come in contact with a negative. That together is insoluble. That's what happens. The barium comes in contact with the chromate. Once that happens, according to our solubility rules, and we can check that in a minute, barium chromate is insoluble. So once they come together, they're not going to dissolve anymore. They actually come out of the solution, or what we call precipitate out of solution. And they form this solid at the bottom. They're going to precipitate out of the solution, and otherwise known as crystallize in some cases. They can recrystallize. It can crystallize, meaning it's a liquid before, it's aqueous, you don't see anything. Eventually, over time, it might take a couple seconds, it might take 20 minutes, but the precipitate will form because those ions will have a chance to interact with each other over time to create the insoluble ionic compound, if there is one possible, which in this case, barium chromate, there is. So that's what a precipitation reaction is. You're mixing 2 soluble ions, or soluble ionic compounds. The ions will basically rearrange until one of the combinations is insoluble. Once that happens, you have an insoluble precipitate that forms. That's it. Any questions on what I just said? I'm going to write that down because that was a very to the point thing. And then you see your solid precipitate is barium chromate. But basically, what would I just say? So 2 soluble ionic compounds are mixed until the mixture of free ions will combine to form an insoluble combination of ions, forming a precipitate. I used combine twice, but yeah. Yeah, question?
Yes.
Yes.
How do you know which one's going to form? Do they have to tell you in the question?
So, good question. So the way you know which one's going to form is by your solubility rules. So we're going to do examples of this right now. So knowing those rules, it'll tell you, all right, now I have the list of ions. Which combination, and it'll only be one combination. Which combination will form the insoluble precipitate? So in this case, you have potassium, barium, and chromate, and nitrate. So if you look at the list, we know that potassium, every potassium is soluble. So anything with potassium, that's exit out. There's no way that potassium could be in our precipitate solid. Same thing with nitrate. Nitrate is always soluble. If you look at here, always soluble. Cross it out. The only thing left, barium and chromate. So look at, let's see if we see anything here. Oh wait, might not be. So here, no, it's not chromate, but barium is soluble with that. Oh, well, I guess these rules aren't really that comprehensive. It doesn't cover every single ion, but by process of elimination of knowing the base, this is why I say, okay, there are a lot of solubility rules. This is the common ones. If you know these, you should deduce every other one from it. Like we just did, where you have, obviously barium and chromate are not listed in this thing. If you want to get an extended version, they might be listed, but it's a lot of crap to remember. So if you know the basics that every time you have potassium, every time you have nitrate, they're soluble, then by process of elimination, barium and chromate would be not soluble if you know it's a precipitation reaction. Now, sometimes if you have a reaction, I'm glad you asked this question. If you have a reaction that does not form a precipitate or does not have a solid, an insoluble ionic solution, or ionic compound that forms, it's simply known as no reaction. So if I, for example, let's see, get my pen. If I add, KNO3 plus NaC2H3O2. These are everything that's soluble. So, all right, yeah, I think that's right. Yeah. So this is potassium nitrate, soluble, sodium acetate, soluble. If I put these together in solution, there will be no reaction. The reason why is once they're in the water, they'll be split apart into K plus, NO3 minus, Na plus, C2H3O2 minus. And there will be no reaction because any combination of these together, of anion cation, will create a soluble ionic compound, or yeah, a soluble ionic compound, meaning it will split apart immediately again. And there will be a net gain of no solid particulate. So that's a good question. So hopefully that makes sense, that in precipitation reactions, it's not just adding two ionic components together. That's not it. It's adding two ionic compounds that once they rearrange, there is an insoluble solid product. So that's the important part. Okay, any questions? No? All right. So we did that already. Okay, so here we go. Now, just also to your question, predicting the precipitation reaction. Now, it's basically you're switching the ion. If you have a reaction, let's say you, so let's say you're given a reaction. you're given this. All you do, you don't have to really rearrange all the ions because you know how they started out with, and you know they started out soluble. You basically just switch the cations, and you see if the result is soluble or not. And then you balance it. So these are also called double replacement reactions, where all you do is basically switch the cation. See how it's like AB plus CD? You switch the A and the C, you get AD plus CB. Same thing. So you're switching the cations, and you end up with barium chromate and potassium nitrate. And then you have to balance it, of course, but this is called the overall formula equation. And in the precipitate, you have your barium chromate, and then you have this thing called spectator ions, which we'll talk about in a second. Basically, the ions that aren't reacting to create the precipitate. Okay, so is there any questions up until this point? Because the next thing we're going to do is the net ionic, complete ionic equations, which is kind of tedious and is important, though, to represent these reactions. No? Okay, moving on. So there are two types of equations, or actually three, that I expect you guys to know for dealing with precipitation reactions. The first one is what we call the overall formula equation. I'm going to copy that. So the overall formula equation, which the easiest one is what you start out with. Nope. It's the overall formula equation. So that's this one. Basically, you add A and B, and you flip their cations, you balance it, and you get this. Then, if you break that apart, you can get your complete ionic equation, which is another thing that I expect you to know, which is probably the most difficult one. So let's go through it together. And we're going to do examples, I think. So complete ionic equation. Let's take, and also keep in mind, these are all aqueous. AQ, 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 and this one's a solid because it's precipitate. So in the solution, the complete ionic equation is basically how the ions behave when they're in the solution, meaning all of the soluble ions will be lone soluble ions. They'll be by themselves. So K2CrO4, that'll be separated by, it'll be 2K plus, because you can't write K2, it has to be 2K plus, aqueous, plus CrO4 ion, 2 minus, aqueous, plus barium, Ba2 plus, aqueous, plus, there's 2 NO3s, so 2 NO3 minus AQ yields the solid. The solid does not separate. You notice that. Everything else separates except for the solid. Solid cannot separate because in the reaction, in the solution, that is not the behavior of it. It stays as a solid. Then you have the remaining ions, 2K NO3, so it'd be 2K plus, plus 2 NO3 minus. That's the complete ionic equation. Now, before we move on, is there anybody that has any questions? Don't feel like you have a stupid question. Any questions on how I got the complete ionic equation? Because there is a lot of charges, coefficients, pluses, there's a lot going on. So please ask questions on it now. Or later, but now preferably. No? Okay, I'll keep going. All right. Hopefully that means this is very easy. Oh, the question. Can you go over CrO4? Okay. What about it? It's there. So it's chromium. So chromate. Chromate is an ion. Is a polyatomic ion. Oh, the charge. Oh, how you got the charge? Oh, the charge is just one of the polyatomic ions. So good question, because it's not one of the ones that is a common polyatomic ion, but if you know that it is an ion, you should be able to get the charge from it by seeing what it's paired up with. So you see it's K2CrO4. So K2, you know potassium's +1. There's 2 of them, +1, +2, and then chromium, chromate, the whole thing, chromate, will have -2 then. But it is one of the polyatomic ions, and you don't need, that one's a little bit more of the uncommon ones. There's chromate and then there's dichromate. Dichromate is actually Cr2O7, but those are different ones. But anyway, they're just polyatomic ions.
I have a question.
Yeah, what's up?
So how does the first equation, the overall formula, relate to the complete ionic equation? Does that mean, do you like start with K2CrO4 and then BaNO3
Yes.
and then end up with
right? So the first thing you write, so the first thing you write is the complete one. Sorry, not the complete one. The formula equation. This one, the top one, right? That's the one that you balance. That's the one that's easier that you've seen it before. It's easy to work with. Then you split this up into the complete ionic equation. So you get one.
Okay, so which side did you split where? So like which side of the overall equation did you split to get the ionic equation?
Both sides. So if you look at, this is the left side. Let's take a look at the left side. K2, 2K plus. CrO4, CrO4 2 minus, plus barium, Ba2 plus the NO3, 2NO3. That's the left side here. It's the same exact thing. It's just split up by ions. Then yields the right side. The right side is, we'll ignore this for now, but it'll be 2K plus and then 2NO3 minus. Got that. And then the solid. The solid is the only thing in the complete ionic equation that is not separated into ionic components, because in the solution it will be a solid. It's not going to be Ba2 plus CrO4 minus or 2 minus. It'll just be by itself. It'll be a solid. So we split up both sides. And the only thing you don't split up is a solid. Does that make sense?
Yeah, thanks.
Okay, cool. So then the reason why you do, I'm sure you're thinking, what the hell's the point of that, right? The reason why, and that's what I thought when I first learned this. I'm like, this is stupid. The reason why is because to get from the complete ionic equation to the final goal, which is the net ionic equation, you need to cancel out everything in the complete ionic equation that is similar from the left and the right side. Just like a math problem. So we can do that right now. And what we're crossing out is what we call our spectator ions. Our ions that are in the solution, but do not directly contribute to the precipitate compound. So let's do that. 2K plus. It's on the left, it's on the right. CrO4 2 minus, it's on the left, it's not on the right. So we leave it. Barium, same thing. It's in the compound on the right, but it's not by itself. 2NO3 minus from the left, from the right. Our answer would be Ba2 plus, or these two, basically this, plus, or yields this. That's exactly what you get. Barium 2 plus, chromium, chromate 2 minus, yields barium chromate. So, and here you go. While writing the net ionic equation, ignore the spectator ions. Not ignore them, they cancel out. You see how they cancel out. If they don't cancel out, you probably did something wrong in the complete ionic equation. So does that make any, that's like the whole enchilada. That's how we bring everything together, getting this net ionic equation. Any questions on that? No? So I'll write down the definition. So the spectator ions. Spectator ions are ions that do not participate, or that are not in the precipitate product. Okay, good. So now here's another representation of the solubility rules. It's really the same thing I said before, the same list, but it's just, I don't like this list. That's why I put the first list. It's saying like the exceptions or whatever, but that's another list you can look at. Okay, so this is another example. You have Ki, potassium iodate or iodide, and it's soluble. You have your K plus and your I minus, and you mix it with lead nitrate. So lead nitrate is soluble because we know that all nitrates are soluble. You see here's the original compounds. The original cations are Ki, Pb, NO3, 2. What would happen is in the reaction they switch and they create these possible products. So we're going to do this one. We're going to do this one in a separate sheet, just so you can get the idea of the whole process. All right, so here's our reaction. So first, let's write the reaction. Let's write the reaction. Let me get a pen. I'll use blue. Thickness, I'll use 2.5. All right, let's write the reaction. We have Ki aqueous. And for this case, for precipitation, it's important to write the states, either aqueous or solid, or if you have liquid, liquid, but mostly it's gonna be aqueous or solid. Because if you don't write solid, the reader isn't gonna know which one is the precipitate. So PbNO3 2 AQ, and it reacts and it makes, you switch the cations, you get KNO3. That's going to be aqueous, right? Because NO3 is always soluble, K is always soluble, plus PBI. So it's going to be lead is a 2+ charge here. So it's going to be PBI2. It's going to be solid. Why do I know it's a solid? Because it's lead, because it's not nitrate, it's not, the anion isn't nitrate, acetate, there's no potassium in there. It's lead, it's one of the weird ones, and it raises the red flag, so it's probably, or it's definitely the precipitate. And also, the other product is not the precipitate, so it's gotta be. So all those reasons together, you can deduce that information. So now, does everyone understand first? I know this might be difficult for some of you. I'm not sure, maybe. But is there any questions on how I went from the picture to the equation? Because I expect you to do the same, to be able to do the same thing. So if you have any questions on how I did that, let me know. No? All right, let's keep going. So now we can do, there you go. So now we can do the balancing. So K, there's 1 K here, 1 K here, we're good. Iodine, 1 iodine here, 2 iodines there. Make this a 2. Now you have 2 Ks, 2 K here, 1 K here. Make that a 2. I think we're done. Yep. So let's double check. PB, 1 here, 1 here. NO3, 2 here, 2 NO3, we're good. All right, balanced. Next, we need to make the net ionic equation. I'll put net ionic equation. So I'll write that in a different color. I'll use green. So now we need to split apart the ions, and I'll do this slowly. Aqueous, that means it's split apart. Ki, it'll be 2 K plus AQ, It's very easy to forget something small. Plus 2I minus AQ plus, now we're on PB, it's going to be PB2 plus AQ plus 2NO3 minus AQ. That's the left side. Is there any questions on the left side? I basically took everything that was soluble in the beginning and split it apart into its ionic components. No? All right. All right, next. The thickness of this marker keeps changing. All right, so next, I'll write the right side will be over here. Let's take 2, so KNO3 we know is the soluble part, 2K plus AQ plus 2NO3 minus AQ yields, or not yields, we already did yields. All right. Why did it go back? It always does. It goes back to that. All right. I can change the default later, probably. So then, where's the? There it is. All right. So then, plus the solid. This is the precipitate, lead iodide, plus PbI2 solid. So this is the net ionic equation. Are there any questions on that? We just split apart everything into ions, and we left the solid as a solid. Okay, so now we can do the fun part and write the complete, or sorry, the net ionic equation. Oh, wait, sorry, whoa, that's wrong. No one corrected me. This is the complete ionic equation. The net ionic equation is the last step. So the net ionic equation, we have to cancel out everything that's on the left and right side that is in common. So 2K plus, 2K plus. 2I minus, nope. PB, nope. 2NO3 minus, 2NO3 minus. What's left over? 2I minus AQ plus PB2 plus AQ yields PBI2 solid. So that is the net ionic equation. Now, I could ask you several things about this, about a question like this. It could be an open-ended. I could ask you, balance the equation, write the complete ionic equation, the net ionic equation. What are the spectator ions? What is the precipitate? That's about it. But I could ask some questions, and multiple part questions. Okay, so now that we did this example, are there any questions? And that's still good, so that's good. No questions? All right, let's keep going. All right, so we'll do this one. And this one you can probably tell from looking at it. So in the reaction, AgNO3 plus NaCl yields NaNO3 plus AgCl. What is the precipitate? Anybody want to write in the chat or tell me? Olivia, I asked you the question. What do you think? Don't question it. Be confident. Good. It's confident question mark. That doesn't make sense, but AgCl is your final answer, hopefully. So yes, AgCl, good job, everybody. And good, Nick, because the other one has NO3. And also it has Na, so it's definitely, it's very, very soluble. It's got everything, every mark of a soluble compound. Okay, so good job. So you see that every time you see silver or lead or mercury, it's probably going to be insoluble. That's like a really good go-to, a really good rule of thumb. Unless it's with nitrate or acetate. So good. But the way you should write it is, see, the question is, what is the precipitate? Some people might get confused and write, oh, silver. Silver is a precipitate. No, it's not. It's not chloride either. Because by themselves, they're soluble. But it's silver chloride. So the entire compound is the precipitate. So good. That's a question from the homework, so you're welcome. I have those thrown in. Okay, now this is stupid. We did this already. Basically just...
I have a question.
Oh yeah, what's up?
So in this equation, like if you were given this, would there ever be a case where, silver or chloride itself would be the precipitate, or would it always be the compound that it forms?
Always be the compound, because every ion by itself is soluble. So,
okay.
Yeah. Well, if you're dealing with sometimes a single replacement, like, okay, in redox, that's different. Because in redox, you could have one thing gets oxidized, one thing gets reduced, and it can get reduced from Ag plus to Ag, the silver, and that's a solid. But that's different than this. That's, if you have ions, it's going to be soluble all the time. So yeah, it's going to be soluble all the time. Okay, don't worry about this slide. This is just saying, like, you can use this idea, or everything we just learned, to do stoichiometry like we learned last week with limiting reactant and things like that. Or did we learn that last week? I don't know, but you know limiting reactant already, so whatever. Whenever you learn that. Okay, so acids and bases. In the rest of the lecture, the remaining 16 slides, it's mostly review. I'm going to go through it a little bit faster because we're almost done. Acids and bases. So acids ionize in water and they form the H+ ion. Bases dissociate and they form OHs, right? And these OHs and Hs are antagonistic of each other. They're opposites. When they come together, you get water. And also, that's why water has a pH of 7. It's exactly neutral because it has 1 part acidic component. I just said but I meant acidic component. And then 1 part basic component, which is the OH-. So yeah, and every single time the acid and base reacts, you get a salt and water, a salt. It doesn't have to be NaCl, it could be a different type, and always water. So we went over that already. And when you added acid and a base, it's what you call a neutralization. So the neutralization means it neutralizes. So you take the acid, it's no longer going to be acidic pH, it's going to be neutral. And you're going to get a salt, which is mostly neutral, and then you're going to have water, which is neutral. So that's how neutralization works. And the net, you could do the same thing. You could do net ionic equation for acid base. And all the time, it's H+ plus OH- is H2OL, liquid. Now, here's a thing what's a little bit different. Whenever you have aqueous, that means it's a solution containing more than one thing. Meaning that its media, its solvent is water. But if you have liquid and solid, or even gas, it's telling you that, or not gas, if you have liquid and solid, that's telling you it's a pure substance and it cannot be broken apart. So in an acid-base reaction, if you were to, well, let's get the net ionic equation for this one. Let's just do another example. Oh, I didn't mean to do that. Pen. Okay, here we go. So let's do the net ionic equation. You have HNO3. Now in solution, it'll be 2H plus AQ plus 2 NO3 minus AQ plus Ca2 plus AQ plus 2OH minus AQ. You can see how this is very tedious. So when you're doing this in the homework, especially when you're writing this stuff in or answering questions about it, make sure you go very slow so you don't mess up a plus, a 2, a 1. There's a lot of different things going on. And then you have Ca2 plus AQ plus 2NO3 minus AQ plus 2H2O liquid. And the reason why we didn't split up liquid is because just like solid, it's considered a pure substance. And just because there's no precipitate doesn't mean that we can't say we can split everything up. So for a liquid, for a pure liquid, a pure solid, or even a pure gas, you can't split this up. So in acid base, that's the only little thing that's different when you're writing the complete ionic and net ionic. So we can finish this off. Let's do that. I'll switch to red for crossing off. And we can cross off 2H plus, nope. NO3 minus, yep. Ca2 plus, yep. And then everything else is the same. So our net ionic equation will be 2H plus AQ plus 2OH minus AQ yields 2H2O liquid. Like that. Yeah, there you go. Yeah, basically the same thing, but for acid-base neutralization, it is a little bit different. Any questions on that? No? Okay, good. So a lot of this is review. So here's strong and weak acids again. Same slide as before. So I put it in the beginning because it tied in better to the beginning than it did to here. I hated the original layout of this chapter. So anyway, so here's what the textbook does to tell you what the strong acids are. They're like, oh, basically they did Hickel, Hibber, High, Hino, Hisso, Hiclo. Ooh, but they don't tell you that acronym. I made that up. So give me credit. But and you see everything else is weak. So the list is not just this, there's a lot more weak acids. But these are the strong ones. And also they forgot HClO3. That's another one. So HClO3 and HClO4, they're very close in strength. So I just count both of them. And they're both considered strong. So, and here's some bases. Ammonia is a very important weak base. And even, I'm surprised no one had this question, that why is it a base even if it doesn't have OH in it? And the reason why is because it produces OH when it's in solution, meaning, and they put that asterisk to tell us that if you add water to it, if you put ammonia in water, the ammonia acts as a base, it gains a hydrogen, becomes ammonium, and then your remainder, because it took a hydrogen from water, the remainder is OH minus. So it, in essence, produces a basic solution. It itself isn't basic, but it produces a basic solution. Therefore, we consider it a base. Okay, so any questions up until this point? We're going to change gears a little bit to acid-base titration, which is, I'll go over it slow. You guys aren't really in lab, so, or maybe you took lab already, so it's not. I don't think there's going to be a question on it on the exam. Oh, there's a question. So then would NH3 only react when in water? It will only react as a base when it's added to water, correct. But there's reactions with other stuff, but it's only considered a weak base in an aqueous solution. Aqueous means with water. Good question. Okay. Next, so acid-base titration. So a titration is an experiment. There's different types of them. This acid-base is the main one. But basically, it is when you know the concentration of one substance and you don't know the concentration of the other substance. But when you react them together, a certain amount of the known substance reacts with an unknown amount of the, when a known amount of the known substance, meaning you know the volume and the concentration, reacts with a known amount, meaning a known volume of an unknown concentration, you can determine the concentration of the unknown. Basically, you can determine the concentration of an acid if you add base to it. That's it. And the way these work is you add base until you get an equivalence point. The equivalence point is when the concentration of H plus and OH minus, meaning the acid part and the base part, is equal. And they're in a stoichiometric ratio where they're completely reacted and their concentrations are equal, most likely. And you have a pH of 7, it's neutral. And then you have a thing called an indicator, which is a environmentally sensitive dye. And I don't mean it's an environmental advocate. It's not sensitive like that. But what that means, that was a bad joke. But what it means is that it's chemically environmentally sensitive, meaning it changes color based on the pH range. So if there's some of them that are pH 7, phenolphthalein or phenol blue, phenol blue, whatever it's called, they change color if they're close to pH 7. So here's exactly what's going to happen. So I
have a question.
Yeah, what's up?
So like that indicator, is that like when I test the amount of chlorine in my pool with like the little yellow liquid?
Yep.
That's what that is? That's
what it is. It's a type of indicator.
Okay, cool.
And some of them, so indicators could be a variety of things. So it's basically a molecular probe in essence. If there's too much chlorine, it reacts with the chlorine and creates a color, or maybe the opposite. There's different types of them, but what does yours do exactly?
So the more chlorine there is in the pool, the darker of a yellow.
Right. So basically it reacts with chlorine, and if it gets to a certain darkness of yellow, all right, there's too much chlorine in the pool.
Yeah.
So that's not necessarily based on pH, but it's based on amount of chlorine. So whatever molecules in there, I think there's several of them. Really, it's probably some kind of cation, honestly.
But then there's another part, which is it's a red liquid that is for pH. There's like two separate sides.
Exactly. So you need to have those two things are important when you're dealing with a pool. You can't have an acidic pool, a pool that's either too acidic or too basic, and you can't have too much chlorine in there either. So the red one is a pH indicator. So that's cool that you use those a lot. I never had a pool growing up. Yeah, I never had a pool growing up. So, but yeah, that's cool. So there are different types of indicators. Some that react with certain substances. Let's say lead in water. That's how they figure out how much lead is in the water. They get a sample of it. They use some kind of indicator solution. It turns a certain color. Oh, that means there is 10 ppm, meaning parts per million of lead in the water. That's too much. And then they send a warning out to everybody. Oh, there's too much lead in the water. So different types of indicators. But for acid-base titration, it's that red solution you were talking about is one of the possibilities. Sometimes it's purple, sometimes there's different types. But they basically change color when there's a pH range, in a pH difference or range. Some of them, they could actually be blue if it's a low pH, or even turn red if it's a high pH, or vice versa. Some of them just have the strength of the color, meaning if it's really light, that means it's a low pH. If it's really strong, that means it's a higher pH, or there's different types. But basically, you put in a drop of indicator into your unknown solution. You have, let's say it's an acid. You have in a burette, this is a burette, you have a known concentration and a known volume of your base. You start slowly, drop-wise, adding your base to the acid until the pH is 7. As soon as the pH is 7, boom, color change. And you might have to mix it around a bit, but eventually the color stays and you get a color change, and that means the equivalence point is reached. And what you can do from that information is you can say, all right, I used 20 milliliters of 2 molar NaOH to neutralize 50 milliliters of the acid. What is the concentration of the acid? And you can figure that out using everything we know so far. We know moles, we know molar mass, we know all that stuff. And we don't know molarity yet, but we're about to learn it towards the end. Okay, so any questions on that? Because we're gonna switch gears to redox again as a review. No, all right. Redox. So oxidation reduction, a review. So oxidation, we talked about oxidation as last class as the oxidation number increasing. Also, it can refer to compounds that you have an increase in oxygen, compounds that lose hydrogen, and that's basically it. Because the other two elements lose electrons. That's the same thing as the oxidation number increasing. Half reaction has electrons as the product, same thing as lose electrons. So if you oxidation, it makes sense adding oxygen. So let's say you have PbO, and then it turns into PbO2. That would be an oxidation of lead. So it adds an oxygen. Or if you lose hydrogens is another example. But yeah, so mainly think that, like we went over last class, oxidation, the number increases. If the oxidation number increases and it goes more positive, that means you are losing electrons. You are losing negatives to get more positive. And that's the key. Then reduction is the opposite. Reduction, the number goes down. Oxidation number of an element decreases, meaning you are gaining negatives. You are gaining electrons. So element gains electrons. And then it's the opposite of oxidation, meaning you are losing oxygens, or you can be gaining hydrogen. Sometimes it's not like all of this has to happen. One of these, I mean, the oxidation number has to decrease or increase. That's a given. For most 99% of the time it happens. But sometimes a compound can just lose oxygen or gain hydrogen and it'll be reduced. So keep that in mind. So oxidation, so in this case, you could think of oxygen and hydrogen as opposites. Oxidation gains the oxygen, gets rid of the hydrogen potentially. Reduction loses oxygen, gains hydrogen potentially. If that's one case. But really the oxidation number is indicative, whether that goes up or down. That's the most indicative of is it being oxidized or reduced. And then as oxidation states, we talked about this already. I'm not going to really go over that too much, but there's the charges. And if an element's by itself, it's 0. And then we know how to go, we know how to figure out what's oxidized and what's reduced. So that's already there. Whatever. I was going to do that example, but we should have a good idea on that. Oh, this is a good one. No, wait. Oh, I want to get rid of. Okay, fine. We'll do this one by hand. Oh, cool. I can do that. We'll do these quickly, just as a refresher. All right, because there's a lot going on here. So, pen. I'm hungry. So after I'm done lecturing, I'm gonna get cereal while you're doing your homework. All right, so let's go element by element and see what is oxidized, what's being reduced. The first thing is always assign oxidation numbers. So H2, hydrogen +1. Since sulfur changes, but we know there is 2 hydrogens +1 +2. there is no net charge, which means the sulfur has to be -2. Oxygen, -2. Nitrogen, it varies a lot like we saw last week, but we know that nitrate has a -1 charge, which it's written right here. If there isn't a written charge, there's no charge. So only when it's written. So that'll help you. So basically what we're doing is 3 times oxygen, which is -6, equals -1. That means nitrogen has to be +5. +5. Hydrogen, now this is a thing that's a little bit different. Even if the element is by itself, if it has a charge, that's its oxidation number. So hydrogen +1. So hydrogen is by itself. You would think, oh, it's 0. No, you have to check the charge. The charge rules everything. If there's a charge, that means that's the oxidation number for that element. But for a polyatomic ion, there's a charge here, but you still have to determine what the charge is on oxygen and nitrogen, or what the oxidation number is. So let's continue. Sulfur is 0, it's by itself. Nitrogen, or oxygen in this case, is -2. Nitrogen in this case is +2. Oxygen -2. Hydrogen +1. Okay, so let's look at sulfur went from -2 to 0. That means it was oxidized. It went up. And therefore, it is the reducing agent, Ra, reducing agent. Nitrogen went from +5 to +2. So it went down. So it is reduced, which means it is the oxidizing agent. Good. Any questions on that one? That's it. So assign the states, determine the changes, and then assign the definitions, either reduced, oxidizing agent, or oxidized and reducing agent. All right, if there's no questions, we'll do this one real quick. So O2 is going to be -2. There's 2 of them. That makes -4. Manganese is going to be +4. HBr, Br is -1. H +1. Br2, MnBr2, Br is going to be -1 again. Mn in this case is going to be +2 because there's 2 Br minuses. Br2 here is going to be 0 because it's by itself. It's elemental form. Oxygen -2, hydrogen +1. All right, I'm glad this example is here, because bromine, in this case, in one case, this bromine and this bromine, there's no difference, -1 -1. But there's 2 cases of bromine, and they both have different oxidation numbers. That's crazy, but that still works. That means it went from -1 to 0, meaning it went up, meaning it's oxidized. Even though not every bromine atom was oxidized, some of them were. Therefore, it's oxidized and the reducing agent. I know what someone's going to ask. So after this, I'm going to answer that question. Then for manganese, you have +4 and -2. It goes down, meaning it's reduced. And that is the oxidizing agent. Yes. Okay, so hopefully that example made sense. Now, I guarantee somebody was thinking, and I was thinking, what if you have 2 cases on the right side where one of them the oxidation number goes up, the other one it goes down? Which one is it? So I don't actually know. I've never seen one, so I'm going to say it's not possible. But I'm sure it is. And I think it's probably both. Like it's oxidized and reduced. It's both, but we'll just say that that's not possible. And it's not going to happen. So yeah. So that's a good example. Okay. Any other questions on redox before we quickly do molarity and dilutions? And that's it. No? Okay, last thing. All right, dilutions. So solution concentration. A solution could either be concentrated or dilute. Concentrated means there is a lot of solute compared to the amount of solvent. If you dump an entire box of salt into a glass of water, that's very concentrated. If you dilute, if you put the same box of salt into a lake, it's very dilute. So that's what that means. And there are ways, we're going to learn about concentration and molarity today in the next slide to quantify concentration. But basically dilutions, the formula will be on the last slide, but basically what dilutions are is we're taking a concentrated solution and we're adding more solvent. Meaning the volume gets bigger, the amount of solute stays the same, and we have a lower concentration. So something I usually use this example every year. Something that I do as a poor graduate student is I dilute my orange juice with water. It's a little bit too sweet, whatever, but you can make one thing of orange juice last twice as long if you dilute it with water, and it still tastes about the same. Maybe a little worse, but I don't really care. So from doing that process of diluting it with water, I'm not gaining more orange juice. I'm just diluting the orange juice particles, the citric acid, ascorbic acid, diluting it into a larger volume. Extra credit if you dilute your orange juice. Not really, because you're gonna lie and say you do.
I think it's just healthier.
I think it is healthier. Yeah, you get less sugar per cup. Yeah. Yeah. Okay. So molarity. So the definition of molarity is very simple. It's the amount of solute in moles, so the moles of it, divided by the liters of your solution. So for example, if you had, let's see, 58 grams. So 58 grams per mole is the molar mass of NaCl. If you had 58 grams of NaCl, put it into 2 liters of water, what's the molarity? First, you would take 58 and divide it by the molar mass of NaCl, which happens to be 58, you get 1 mole. Divide that 1 mole by 2 liters, you get 0.5. So 0.5 is the molarity. So that's what this is, a 0.5 molar solution of NaCl. Yeah. So yeah, that's basically it for that. We'll do these examples now. Yeah, we'll do one of them. Do one of them. So, okay. How many, because I don't want to give you all the answers to the homework, but let's see. Change the thickness again of the marker. All right, how many moles of H plus are in 216 milliliters of 0.49 molar nitric acid? Okay, so let's write the equation, plug and chug. 0.49 molar equals X amount of moles. And this is moles of HNO3 over, because the solution is HNO3, 0.216 liters. Note how I changed the milliliters to liters. And then you multiply, and I'll do that on my phone's off. I didn't want to, if my phone used up too much Wi-Fi or something and cause it to disconnect, I didn't want that to happen. All right, so you do the math there and you get 0.105, 0.106. So 0.106 moles of HNO3. Now the question's asking for how many moles of H plus? Now, once nitric acid, there's many things you have to think about. When nitric acid is, first of all, Hickel, Hibber, High, Hino, it's a strong acid. It dissolves, it ionizes into H plus and NO3 minus. If it's this many moles of HNO3, there is 1 mole of H per 1 mole of NO3 and per 1 molecule. So it's a 1-to-1 ratio, and your answer is 0.106. But the answer is not 0.106 because I got that for this answer. Sometimes you might have how many moles of NO3 are in MgNO3 too. In that case, it's double. So it depends on what the formula is. And there's a question, I will answer it. Okay, good. Good job, Marie Madeline. 0.106, awesome. So,
Professor,
yeah.
why do you have to change the unit?
Oh, because the definition of molarity is the amount of solute in moles divided by your liters of, it has to be liters of solution. So that's why you always change it to liters. Okay, we'll do one more. So what is the molarity of the nitrate ions? So that's key, nitrate ions, when 0.56 moles of barium nitrate, BaNO3, dissolved in enough water to make 4 liters of solution. All right, so let's set this up. So we don't know the molarity equals 0.56 moles of BaNO3, and that's going to be 4 liters. So do that math, and I'm going to get, let's see, 0.56 divided by 4, 0.14. Yeah, so 0.14 molarity. This is the molarity of BaNO3. That's important. So now we know that, but it's asking for what is the molarity of the nitrate ions. So we know the molarity of barium nitrate, where there's 2 of them, is 0.14. So in that solution, you double it, 0.28 molarity of just nitrate ions. So your answer would be 0.28. And the rest, the next one I'm not going to do, you can do on your own. It's basically the same thing, same kind of question, but it's NO3. So and it's asking for, oh, it's asking for aluminum, so it's not too bad. Okay, cool. Any questions on those? We're almost done. One more slide. Any questions? No? All right. The next, dilutions. So there is a dilution formula. The dilution formula is M1V1 over M2V2. So what that means is your molarity of solution 1. So I'll put molarity 1, volume 1, molarity 2, volume 2. So yeah, so you take an initial solution, let's say you have 0.25 molar and you have 1 liter. I want to dilute it to 0.1 molar. How much volume do I need in the solution? Or how much volume do I need to add? First, you would solve for V2 and then subtract the 2 volumes. So there's a lot of work you can do with dilution formulas. So the best way to teach it is, again, through example. So let's do a couple of examples using that equation. Also, these 2 equations, dilutions and molarity, will be given on the exam. So I'm going to write down our equation, M1V1 equals M2V2. So calculate the molarity. Yeah, there's 2 things going on here. So we're going to calculate the molarity of a calcium hydroxide solution that has been prepared by 2.44 grams of calcium hydroxide in water and diluting it to a final volume of 3 liters. Oh, that's not really dilution. We'll solve it, whatever. I don't think that's going to be using this equation, but okay. So 2.44 grams of calcium hydroxide So calcium hydroxide is CaOH2. The molar mass of it, I don't know off the top of my head, so molar mass CaOH2 is 74. So we got 74, the 2.44 divided by 74, 2.44 divided by 74 equals 0.033. So hold on a minute, where's the thing? Here we go. 0.033 moles. They're asking for the molarity of it. So this is another, I don't know why I put this here. It's another molarity question. But basically you're taking that 0.033 moles, dividing it by the total volume, which is 3, and you get probably 0.011 molarity. Okay. This is another one. Calculate the molarity of hydroxide ions in a solution that's been prepared by dissolving 88. So you'd find the moles again, divide it by the liters, and you get your answer. I'm an idiot. I probably, when I was making these slides, I was like, oh, it says diluting. It must be a diluting problem. So it wasn't though. But let's do another, I'll make one up. So let's say you have a 1.5 molar solution of H2SO4, and you have 50 milliliters of it. And you want to dilute it to make it 0.10 molarity, because that's a really strong acid. That's too strong. You want to dilute it, what will be the final volume? So here's what we do. You have your M1, which is 1.5, your V1, which is 50. Now, here's the thing. For V1 and V2, it doesn't matter, like the molarity formula, it doesn't matter if they're in liters or milliliters. That's key. It only matters if they're the same on the left and the right side. So I could put 50 mils there, and then my M2 is 0.1 molarity, and the volume we need to get there is unknown. So we divide this by 0.1. So I'm too lazy to do math. So 1.5 times 50 divided by 0.1 is probably 750. Yes. So V2 equals 750 milliliters. That's the total volume, right? If the question was asking for how much volume should I add to get to that 0.1 molar solution, you do 750 minus 50, or it would be add 700 milliliters. So yeah. Okay, cool. So is there any questions on that or anything else? I think that's the last slide. What is this? More example. Yeah, good luck. That's more examples. I think that's from the homework too. So yeah. Okay. Is there anything else? If there isn't anything else, I'm going to stop the recording and